Hi, this is Edmund, and this is going to be a quick explanation of expectation maximization, which is essentially used to find the parameters of a Gaussian model, which serve as your clusters. So, first of all, in order to understand what this is that we have to have an overarching understanding of what clustering is in general. So first, there are two main types of clusters. There's hard clustering and there's soft clustering. For example, in k-means, which is the most commonly used, you'll find that points are hard assigned to either one cluster or another. You're either 1, you are part of a cluster, or 0, you are not. So in that case, if it is ambiguous as to which cluster a point belongs to, then it's really difficult to draw an accurate interpretation from that. A Gaussian form of clustering is able to solve that because Gaussians, which are essentially based off of which is essentially just a normal distribution, which is based on probability, it gives you a lot more information about a point because Gaussian distributions are essentially telling you the percent chance that a point belongs to a certain thing. So this is a two-dimensional representation of what a Gaussian would look like. You can see that there is a mean mu in the center, and then you also have a standard deviation that's going across this way. When you take it across to 3D, you'll see that there is a high density in the middle, but then much lower density and a really quick drop-off as you go to the edges. So, how does the EM algorithm solve these things? Well, first you have to understand is that each cluster, such as in here, has two parameters. You have your covariance, or your standard deviation, and you have your mean. So if you know these two parameters, you can easily find which points belong to which one. For example, as you can see in this video, you can see that each of these points, if you know which cluster each point belongs to, blue or yellow, you can easily find the variance and the mean of each Gaussian cluster if you know that there are two clusters. However, what if you don't know which point is assigned to which, but you do know the parameters? Then in that case, you can easily draw the correct Gaussian distribution, which they are not correct. This is the first iteration here, so they have not converged yet. But if you did know which point belonged to which, then you could easily draw the correct one immediately, and you can get your information that way. Well, what if you know neither of those because you need one to find the other? Well, that's where expectation maximization comes in. Well, you see, the EM algorithm essentially first creates two, for example, you can create two clusters randomly with random mean and covariance. Then, similar to k-means, you will assign probabilities for each one. Then you can take the weighted average of each point and divide it by, like, say, the means of all of them. I'll be honest with you, I'm not completely familiar with the math, but the basic concept is very similar to k-means, in which you recalculate which cluster, quote unquote, it belongs to, which in this case would be a probability, and then based on which points belong to which one, you can redefine your parameters so that it fits them all better. However, in this case, you know that the mass of each point influences the parameters of each and every cluster. For example, the points over here would influence the drawing of the second blue Gaussian a lot more than the yellow one because they immediately seem to fit a lot better with the blue one. However, they still impact the yellow one slightly. As you can see in this point, which is much closer, it has a much larger shade of yellow, which indicates that it has a larger weight on it. So once you calculate it, once you find your better version of it, you then do it one more time to see which points fit into which one, then you iterate it, process over and over until it converges, which is the same idea as k-means, however now you're doing it with probability. So why is this useful? Well, this is especially useful, as I mentioned earlier, because in some cases data points are extremely ambiguous as to which one they belong to. So here's an example problem. For example, if you're looking at the average heights of people from different ethnicities, then you are expecting different distributions of height for each ethnicity, even though it's going to be a normal distribution for each one. This means that you have to have you have to, if you're trying to like say cluster all of them, then you need a weight factor for each different ethnicity, because each one is going to have a different distribution of heights to begin with. So when you're like, basically this is especially useful when you're trying to figure out, say, the chances that someone will belong to a certain group, or the chances that someone will do something and then will do something else as a result of that information. And this is basically better than k-means because it is more flexible in that sense. However, k-means is probably more efficient because it requires less intensive calculations. So even hopefully after this video you have a general understanding of the general concepts, even if we don't understand the math. Hopefully in the future maybe we will, but because the library is already written for us, we just need to understand where it's useful and how it can be used, and hopefully we can apply it, and I hope that was helpful.